Dear all, I am Dr. V. Malati, Associate Professor, ECE Department, SR University, Varangal. So this lecture is how to simulate blood glucose level measurement using biosensors. This experiment simulates a glucose oxidation, that is GOX, electrochemical biosensor, where glucose reacts with enzyme and produces H2O2. And H2O2 oxidation generates current. And this current is proportional to glucose concentration. Therefore, this code explains calibration curve and it shows linear relationship between glucose concentration in milligram per dl and then sensor output current in microampere. Then linear regression. It finds calibration equation using I is equal to MC plus B. It is the standard formula where I is the current, C glucose concentration, M sensitivity, B baseline current. So the unknown sample estimation is done. It uses inverse calibration equation to estimate glucose level. And then we get dynamic response. It may show exponential response behavior of biosensor. And then what will be the expected output? It will be the calibration curve graph and then calibration equation and estimated glucose value. Then dynamic response plan. This program simulates how an electrochemical glucose biosensor works. So in real life, glucose reacts with glucose oxidase enzyme. Reaction produces electrons. These electrons generate a measurable current, and this current is proportional to glucose concentration, and thus this code models this process mathematically. Now first we will import required libraries. Import numpy as np. So Python library. Then import matplotlib.pyplot as plt. Then from sklearn.linear underscore model and import linear regression. Now, what will be the meaning for these three? So we are using numpy and it is used for numerical calculations, arrays and random noise generation. And this matplotlib library, it is used for plotting graphs. That means calibration curve and response curve. Then linear regression. It is used to find best fit line, that is calibration equation. Then sensor parameters. Here what we have given, sensitivity is equal to 0.8, that is microampere per milligram per dl. Then baseline underscore current, it is equal to 2. That means microampere background current. Then noise underscore level, it is equal to 0.5 noise in microampere. These simulate real biosensor characteristics. Then sensitivity 0.8 microampere current per 1 milligram per dl glucose. Then higher sensitivity means more responsive sensor. Then baseline current. Even with no glucose, sensor shows small background current, and then due to electrodes and electronics. Then noise level. Real sensors have noise. 0.5 microampere random fluctuation is added, and then generate glucose samples. Glucose underscore concentration, it is equal to NP dot linspace open bracket 50 comma 300 comma 20. That means it is in the range of mg per dl. This creates 20 glucose values between 50 mg per dl, which is low, and then 300 mg per dl, which is high. This simulates lab calibration samples, and then sensor current simulation. Sensor underscore current. It is equal to sensitivity into glucose concentration plus baseline current plus NP dot random dot normal 0 comma noise underscore level and LEN open bracket glucose underscore concentration. And what is the meaning for this code, this line of code? This is the most important equation. The formula used is equal to I equal to S into C plus I baseline plus noise. And what is I? It is sensor current. S is equal to sensitivity. C equal to glucose concentration. Then NP dot random dot normal 0 comma noise underscore level comma size. Now what is the meaning? It adds random measurement noise. Then plot calibration curve. So PLT dot scatter open bracket glucose underscore concentration comma sensor underscore current. This shows glucose in mg per dl will give current in microampere. If sensor works properly, it points from a straight line. Slight scatter due to noise. This is the calibration curve used in the real biosensor labs. Then linear regression. The calibration equation and then reshaping data. X is equal to glucose underscore concentration dot reshape, that is -1 comma 1. Y equal to sensor underscore current dot reshape -1 comma 1. The machine learning models require 2D input. That means reshape -1 comma 1 converts one-dimensional array to column format. Fit model. Then model equal to linear regression function. Model dot fit open bracket x comma y, and this calculates best fit straight line where m equal to model dot coef underscore sense underscore, and this gives the sensitivity. B equal to model intercept underscore, and it give the baseline current. Then print calibration equation. So current in microampere, it is equal to M into glucose mg per dl plus b, and this is exactly how real glucometers are calibrated. Then predict unknown sample. Unknown underscore current is equal to 150. This is example measured current in microampere. Suppose sensor measures 150 microampere, then we can reverse the equation C equal to 1 minus D by M, and then predicted underscore glucose. It is equal to unknown dot current and unknown underscore current minus intercept divided by slope, and this estimates blood glucose level, and then this is how glucometers calculate glucose from measured current. And then dynamic time response simulation. Time equal to np dot linspace open bracket 0 comma 10 comma 1000, and at 10 seconds. It simulates 10 seconds of measurement. Step input and step underscore glucose is equal to 120 milligram per dl. It is the step input. Suddenly, glucose becomes 120 milligram per dl, and then exponential sensor response. Response underscore current. It is equal to sensitivity into step glucose into 1 minus NP exponential minus time by 2 plus baseline underscore current. This models real biosensor behavior. The term 1 minus e power minus t by t. So time in t divided by tau. This give slow rise. This will give slow rise. Time constant equal to 2 seconds. This tau equal to 2 seconds. Then gradual stabilization. Real biosensors do not respond immediately. Then final plot. It shows time in second with current in microampere. You will observe exponential rise and then steady state after few seconds. Then what this experiment teaches? Sensor parameters. It will show the biosensor characteristics. Calibration curve. It will show current versus glucose relationship. Then linear regression. Finding calibration equation. Unknown prediction. It will give glucometer working principle. Then time response. It will give dynamic sensor behavior. And then what will be the complete mathematical model used? First one static model, I equal to SC plus I naught plus noise. I naught plus noise. And then inverse model C equal to I minus I naught divided by S. Then dynamic model I of t is equal to SC 1 minus e power minus t by tau plus I naught. Now, after simulation, what we will get? See, here sensor current in microampere versus glucose concentration in mg per dl. So, sensor data, these blue dots show the sensor data, and this curve is known as biosensor, glucose biosensor calibration curve. The calibration equation current in microampere it is equal to 0.798 into glucose in mg per dl plus 2.415. The unknown sample measurement. So measured current gives 150 microampere. Estimated glucose level is equal to 184.89 mg per dl, and then dynamic response of glucose biosensor. It gives current sensor current in microampere versus time in second. So from this we can get blood glucose level, and then electrochemical glucose sensor simulation with Google Colab research. So we are first importing the Python library, and then it is abbreviated as NP. So Python library is imported, and then matplotlib.pyplot as PLT. So wherever we see PLT, this word is able to plot the graph. So graph in the sense it may be in the form of curve, one parameter versus another parameter, or else histogram, or else bar chart, bar graph, and box plots also. And then here we are giving the sensor parameters with sensitivity already defined, it is equal to 0.8. So these are all the standard value, accepted value, and then baseline underscore current. It is also a standard value, accepted value. It is equal to 2 microampere, and then noise level is equal to 0.5. So normally it will be very low in amplitude. So less, very low amplitude in amplitude of noise level, and we are considering. And then sensitivity, it is equal to 0.8 microampere current per 1 mg per dl glucose. So that we should know. So 0.8 means it is measured microampere also okay, but it is measured under 1 milligram per dl glucose. And then baseline current, even with no glucose, sensor will show small background current, and then it is due to electrodes and electronics. Then noise level, the real sensors have noise when they are observing the input and giving out the corresponding output. So we will get definitely some amount of noise from the sensor functioning, and then 0.5 microampere random fluctuations added. So it is due to the body muscle movements also. And then it will generate the glucose samples using the formula glucose underscore concentration. It is equal to NP dot length space open bracket 50 comma 300 comma 20. It will create 20 glucose values between 50 mg per dl, which is considered to be low, and then 300 mg per dl, which is assumed to be high. This simulates lab calibration samples. And then how to get sensor current. Using the formula sensor current is equal to sensitivity into glucose concentration plus baseline current, and then NP dot random dot normal 0 comma noise level LEN glucose concentration. And this is the very important formula, and the formula used is equal to I is equal to, so it is in word form it is written, actual formula is I equal to SC plus I baseline plus noise, where I is the sensor current, S is equal to sensitivity, C is glucose concentration, and then NP dot random dot normal open bracket 0 comma noise level comma size. So it adds random measurement noise, and then we have to plot a calibration curve. PLT dot scatter open bracket glucose underscore concentration comma sensor underscore current comma color is equal to blue, label is equal to sensor data, and then plot dot x label. So x axis glucose concentration in mg per dl, and then y axis sensor current in microampere, and title given to this graph is glucose biosensor calibration curve, and then we are using the grid for uh, plotting the graph, and then plot dot legend. So plt dot shows in the final diagram, I mean graph will be visible, and then for linear regression calibration x is equal to glucose concentration dot reshape. It is from -1 to +1. Similarly, y equal to sensor underscore current dot reshape. It also varies from -1 to +1. The machine learning models require two-dimensional input. Therefore, reshape open bracket -1 comma 1 converts one-dimensional array to column format, and then fit model. So model is equal to linear regression. So model dot fit x comma y. This calculates best fit straight line, and then what is the formula? It is equal to I. So current is equal to MC plus B. MC plus B. Where M is equal to model coefficient, uh, which is giving the sensitivity, and then B equal to model intercept. It is giving the baseline current, and then we have to print the calibration equation. So current in microampere, it is equal to m into, that is model coefficient, glucose mg per dl plus b. So this is exactly how real glucometers are calibrated. And then we have to predict unknown sample. So unknown current is equal to 150. So depending on the current, it may measure the glucose level available in the blood. So we can reverse the equation. C equal to 1 minus B by M. So predicted underscore glucose is equal to unknown current minus model intercept divided by slope. So this estimates This estimates blood glucose level. This is how glucometers calculate glucose from the measured current. And then dynamic time response is simulation. So time equal to NP length space 0, comma 10, comma 1000. So at the rate 10 seconds, it simulates 10 seconds of measurements. The step input is glucose underscore glucose, step underscore glucose, it is equal to 120. Suddenly glucose becomes 120 mg per dl. The exponential sensor response. Then response underscore current is equal to sensitivity into step underscore glucose plus 1 minus NP exponential minus time by 2 plus baseline current. And this models the real biosensor behavior. This term is written as 1 minus e power minus t by tau. It gives a slow rise and then time constant is equal to 2 seconds. It is giving the gradual stabilization. Real biosensors do not respond immediately. And final plot we will get time in seconds, which is giving the current in microampere. We can observe exponential rise and steady state after few seconds. And this experiment concludes with the sensor parameters, and the concept behind the sensor parameters are we can understand the biosensor characteristics, and then calibration curve. Calibration curve where calibration curve, it will give the current versus glucose relationship. Then linear regression, we can able to find calibration equation. Then unknown parameter, unknown prediction, it will the glucometer working principle we can understand. And then time response, it will give the time dynamic sensor behavior. And finally, what are the equations we are using in this concept? Static model, which is equal to which is the current I is equal to SC plus I naught plus noise. And then second one, inverse model. So C is equal to I minus I naught divided by S. So and then dynamic model, it is current, it gives the current which is the function of time, and it is equal to Fc and 1 minus e power minus t divided by tau. Tau is the time constant, and it is added with the baseline current I naught. In this way, we can learn we can learn from this experiment how glucose reacts with the enzyme and produces H2O2. This H2O2, it is the glucose oxidase which is generated by the electrochemical biosensor, and H2O2 is the oxidation which is generating the current, and therefore we are getting the current which is proportional to the glucose concentration present in the unknown sample blood. So we are getting this, finally we are getting calibration curve linear regression. Thank you.